Hello guys, so in this wait 1 2 3. So this is the part 2 of this problem, the maximum product of splitted binary array. So we have already discussed the example in the another video, part 1, in which we can see that we have array, right, in which we will binary tree, right, in which we have to split from here and from any other position, and we have to make two subtree, right, subtree 1 and subtree 2, right, and then we have to find the sum of these two, and then we will do multiply like 11 into 10, and then we have to return it as 1110 as a output, correct? So let's see the approach 2, in which we will see that the two pass DFS algorithm. Okay, so the intuition is here to, instead of putting the subtree 1, right, we have give here, this is the subtree 1, right, and uh, in the last example what we used to do, we used to pass subtree 1, right, and then we have to do sum into a separate list, right, and we can do separate tree summing traversal, right. So instead of putting subtree 1 sum subtree 1 sum into a separate list, right, we can do two separate subtree summing traversal, right, we will do, and we will make sum and we will add there. So what we will do, we'll first we have to do calculate the sum of the entire tree. We will do the sum of the entire tree, and then we will make the product we will get for each subtree, right, product with the each subtree we will do, right. So let's understand here. So we will start with the, we will take a variables best, and we will traverse from the subroot, right, subroot, and it will this is the recursive helper, right, in which the past subroot will pass here, and we will take non local based, and that non local based we have to traverse from the root, right, and from the root it will go to left root and right of the root. We will calculate left sum and right sum, then we will find the total sum, right, the right sum plus left sum, right sum plus left sum, and left, right, and plus root value, right, and we will have the product, right, similarly we have the product, and then what we will do, we will multiply with the total into the subtree 2, right, that we will traverse uh, each node, right. And the best, what we will find, we will take from the maximum, which one is maximum, the best or the product, and that will return as a total sum, and similarly we will do recursive again for the subroot, and we will return final the best, right. So in this way we have to traverse, right, internally we have to traverse for each node, and we will calculate, and for each sum what we have to do, we have to do total sum into the each sum of the subtree, and we will multiply, and then we have to store the best, right, and finally we will return the best, and we will do recursively. Let's understand the problem solution here, right. So in the starting what we will do, we will make two variables like maximum product and the total tree sum, two variable with the initial value 0, and then we will, to find the tree sum, what we have to do, we have to pass the tree node, and that is called subroot, right, subroot here. So subroot should be, if that is equal to null, we will return 0, otherwise we will calculate left sum or right sum, right. So this is the just a base case, so that if subroot is going to null, if we are at the leaf node, then we will return 0, otherwise what we will do, we will calculate the left subtree and right subtree, and we will have the left sum and right sum, and each after that, getting the left sum and right sum, what we will do, we will traverse, and we will no, we will calculate the total sum here, and then we will return total sum. In this function is only to get the sum of the tree, right. If we pass the subtree, we will get the subroot total sum, right. Okay, next coming to find maximum product, in which we have to pass the subroot, right, and then how we will calculate. If this is the base case, right, that will remain same, subroot equal to null, then we return 0. Otherwise we will find maximum product, right, maximum product, and minimum product, right, we will calculate. And how we will calculate it? Using the left sum and right sum, right. We will pass this and then we will find the left sum and right sum, in which we will have total sum, right. We will have total sum, in which left sum plus right sum plus subroot plus val, right. Then we will get it the total sum. And total product, how we will get it? We will get it like, we will multiply total sum into total tree sum minus total sum, right. Total tree sum, we have the total tree sum, right, minus tree sum, right. So from here we have already got the total sum, right. And total tree sum, how we will get it? We will have left sum plus right sum and plus tree root, right. And that we have the total sum now, right, here, total sum. And finally we will get the from the maximum, which one is maximum, total sum or maximum product, and we will update about maximum product. And in this way we will do recursively, and we will finally return total sum. We will update total sum and we will return total sum. So now maximum product is here updating each time for each node, right, each subtree, you can say. And how we'll calculate the max product, right. To get the max product, you have to get total sum of the tree, total sum of tree. How will give? You have to pass tree sum and you will get your total sum. And to find the maximum product, what you have to do? You have to pass find maximum product, right, and you have to pass the root. You will get the maximum product from here, this line, right, this line. So you will have the data here. Your data is now ready. Now what we will do? We'll do maximum product into 10 to into the modulus, right, and then we will return the total sum. So in this case also we will have on square, oh sorry, on and on time complexity, both will remain same, because we have to do each recursive function will visit all the nodes of the subtree, right. In the next program we will see the advanced strategy for dealing with 32-bit integers, and we will see the uh, this approach. Okay, so thank you. If you have any doubt, please ping me in the comment box. So let's understand the another approach of the maximum product splitted binary tree, in which we will see that approach 3, in which we are going to understand the advanced strategy for dealing with 32-bit integers, right. So 32-bit integer, it is saying that this is an advanced bonus section that discuss a way of solving the problem using 32-bit integers. So it's not essential for an interview, although could be useful depending on your choice of the programming language. Some of the idea might also help with the potential follow-up questions, and this section assume prior experience with the introductory modular arithmetic. We will additionally assume that 32-bit integer we are looking with is signed, so has a maximum value of what? There is a number, right? This is the number, maximum value. So what if your chosen programming language supports 32-bit integers, right, and uh, you had no access of bit integer library. So could we still solve this problem? What are the problems what we need to address? The above solution rely on being able to multiply two numbers up to 30 signed bit each without overflow, right? Because the number of bits in the product add, we would expect the product to acquire 60 bit to represent using 64-bit integer. What therefore enough additionally with a modulus of this, right? The final product after taken to the modulus will always fit 32-bit integer, correct? So however, we are not assuming that we only have 32-bit integer. when working with 32-bit integers. We must always keep the total below this number, right? Even during the intermediate calculation, therefore we will need a way of doing the math within this restriction. One way to do multiplication safely is to write an algorithm using same underlying idea, that is called modular exponentiation. So if you will see that modular multiplication, we have int a, int b, int m, right? So if the product is 0, right, we will taking product 0 and sum what? A. Current sum is what? A. So we will check if b is greater than 0. What we have? B mod 2 will get the bit, and we will do shift operate. We will do shift b shift and then 1. If b is equal to 1, then what? We have to update our product using the current sum, and we will do modulus with the m, right? If the shift is 1, then we will check the with the modulus and we will return the product. So there is one possible pitfall with this through. We are supposed to return the calculation for the largest product and determine before modulus is taken. For example, consider the following two products. We have product 1 and product 2, and it becomes after the modulus, right? After the modulus, what? This one, and if we are taking the modulus 1, we are taking this one, correct? With the value. So if we were to compare them before taking the modulus, product 1 would be larger, right? Product 1 would be larger, which is correct. But if we compare after, then the product 2 is larger, which is incorrect. Therefore we need a way to determine which product will be the biggest, correct, without actual calculating them. Then once we know which is best, which is biggest, right, we can use our method for calculating a product modulo with this number, right, with this number, without going over this, right? So previously when we see this number and this number before the modulus, right, before the modulus, which one is big? This one is big, correct? This one is big, correct? And this one is not big. But after taking the modulus, what you are saying? This one is big, right? This one is big. So it is saying that we have to determine the which product will be biggest without actual calculating them. Then once we know which is biggest, we can use our method for calculating a product modulo of this 10 to the power 7, right, and without using over this. So the trick is to realize that sum of what? Subtree 1 plus subtree 2 is a constant, but sum of 1 into sum of 2, right, sum of subtree 1 and subtree 2 increases as sum of 1 minus sum of 2 get nearer to 0. As the subtree is more balanced. A good way of visualizing this is to imagine you have x meters of fence, need to make a rectangle enclosed with some shape. You want to maximize the area. It turns out the optimal solution is to make a square. Nearer to a square, the enclosure is nearer to the optimal area it will be. For example, h plus w is 11, and the biggest solution is what? 5 into 6, right? That is 30. So if we have an area in which we have length is what? 10 and width is what? 1. Sorry, length is 1 and width is what? 10. So what we will do? Multiply, then we will get the area is what? 10. But if I have 9 and this is 2, right? Width is what? 9 and 2 is length. So what we will do? Width into length, then it will come to 18. But if we have 6 into 5, right, 6 is the width and 5 is the length, we'll see that width into length is what, 30. So this one is big, right? So a simple way to do this in code is to loop over the list of all the sum, find sum, comma, total minus sum, and pair that has a minimal difference. This approach ensures we do not need to use floating point number. So coming to the program, you can see that, what you can see that here we are taking mode value, initial mode value, then we will have some, we have a list to store all the sum. Then what we will do, we will take a max product in which we will take the node, and there is a function that calculate the total sum, right? Total sum, we'll see that, right? Here you can see total sum. What we are doing, we are calculating left, right, and total sum. We will add on the list and we will return total sum. Okay, so we are at line 32, in which we are saying that total sum equal to trace sum of root and nearest to half is 0. So int a smallest distance, we are taking max value of the integer, smallest distance, right? And for all the sum that we have calculated from trace sum, right, and we have added onto the list, we will traverse for that sum. All the list will move, right, from index 0 to whatever the length we have got till now. So math dot absolute, in which we will have the total sum, right? We have total sum of that, and then we'll do sum into 2, right? Actually we want to do this in a way that doesn't require float, and one way is to minimize the distance into between two halves, right? So what we will do, we'll take absolute value of total sum and sum into 2. Okay, and we will have the distance between. If the distance between is less than the smallest distance, then we will update our smallest distance between. And now the smallest distance is not a max integer value, but a distance between, right? Because it is the smallest, and that we will take that. So nearest to half equal to what? Sum. Now nearest to half we are updating to what? Sum. Why? Because now we are taking modular multiplication, in which we will pass nearest to half, total sum minus nearest to half, and mode a, b, and m. A, b, and m, correct? That we have seen in the previously, this function, right? That is called modular, right? And the same functionality we will apply here. And you can see that product, we have product, current sum, b is greater than 0, then we will take this like that, and finally we'll return the product, right? So in this example you also see that we are traversing all the node, right, node of the tree, and that's why complexity remains same, on, and space is also remains same. So the modular multiplication function has a complexity of what? O log b, because the loop removes one bit for the each iteration until there are none left, and doesn't bring up the total time complexity of O n log b, because b has a fixed upper limit 32 bit and is therefore treated as a constant. Okay, if you not remember this one, right, the shift operators, right, you make a small program and you will see that how the bit is shifting here, right? Or you can ping me in the comment box, I'll ping there. Thank you so much.